Hello and welcome back to Math 208. Today we're going to start looking at area and perimeter of different geometric shapes. So I know most of you know triangles are three-sided figures and, well, what a circle is, although we could go through the technical definition of it. But I want to start this off with just quadrilaterals because these types of shapes, sometimes it's easy to forget those once you've been away from geometry for so long. So let's just review those things. So quadrilateral itself means it's a four-sided figure. That word quad right there, the prefix quad, tells us it's got four sides to it. And it's not going to be concave, all the shapes we're talking about. So nothing's going to look kind of like this when we say four-sided shape. I'm going to try to make that four sides there, pretend like it's four sides. But that indention in, like you took a square and poked in one of the corners or something like that. None of them are concave. We're all talking about convex shapes. So quadrilateral means it has four sides, and then inside of that we've got some that have special properties. The first we'll look at is parallelograms. With parallelograms we have two sets of parallel sides. So let's see if we've got a parallelogram in here. So you can say that you've got two sets of parallel sides. There are other properties to a parallelogram that make it special, like the opposite angles are congruent, the diagonals will bisect each other, and so forth. But as far as the purpose of this class go, just remember it's four sides and two sets of parallel sides. From there you have a rectangle. Now a rectangle is a special kind of parallelogram. So here I have a parallelogram, but a rectangle, I don't know if I can do it with this tool right here. Let me try just drawing out a rectangle. It is a special parallelogram. Both sides are parallel there, but the angles are 90-degree angles in it. There are other things that are special about a rectangle, the most important being that the diagonals, if you draw a line from this corner to this one, it's the same length from this corner to this corner here. So that's one of your special properties you learn in geometry about rectangles there. And then we have a rhombus, which is also a parallelogram. But what's special about the rhombus, let's take that back, is that all four sides are the same length. So let's see if we can draw one of those. That's pretty close. So notice it's still a parallelogram, but all four sides are congruent. And then you have a square. Now notice the square right here is inside of, it's a subset of the rhombus oval right here. And it's also a subset of the rectangle oval right there. So anything that's a square is both a rhombus and a rectangle. So in that case, you have a parallelogram with the opposite sides being parallel, and then you have a rectangle because all four angles are 90 degrees, and then you have a rhombus also because all four sides are equal. So from there we have trapezoids, and this is going out of the world of parallelograms. Parallelograms, remember, both sets are parallel. With a trapezoid, only one set is parallel. So let me get to kind of make some different shapes here. I'm going to get the shape recognition pen. So the typical one you see looks a lot like this on all those posters in the classroom. This is called an isosceles trapezoid. And so trapezoid only has one set parallel. That's if it's a quadrilateral. Isosceles has the sides are going to be congruent right here. That we call those the legs. And then the parallel sides, we call them the bases. Now, if we have a trapezoid that looks like this, that's called a right trapezoid, where you have one right angle. Notice you only have one set of parallel sides, and it's still a trapezoid. You can also have other trapezoids that are not right, like this. Let's see if we can draw one. Well, it didn't recognize it, but these two legs don't have to be congruent and make it isosceles. They could be, as long as you got one set that's parallel and the other set that's not, it's a trapezoid. And there are other properties about the isosceles trapezoid where you can say like the base angles are congruent, the diagonals are congruent there. But we're not going to get too much in that. I just want you to know what a parallelogram is and all of its, the things underneath it, what a trapezoid is, and what a kite is. So a kite, you have none of the sides are parallel, but there's some special properties to it as well. So a kite kind of looks like what you would think about when you see, Let me try redrawing that. When you see a kite in the sky, that's stereotypical kite, not all the fancy ones they have out there. That's closer to a trapezoid. Let's throw that in the trapezoid area. See how those two sides are parallel? Try one more time. See your kite. Yeah, it's closer to it. So on this case, you have two sides that are adjacent right next to each other and are congruent, and then another two down here that are congruent. You can even say that the diagonals are perpendicular. So rhombus also holds that property where the diagonals are perpendicular. So it's almost like we were just drawing a kite out there. So that's a kite. We're not really going to talk about the area or perimeter of a kite today, but it's part of the quadrilateral family, so I put it in there. So that kind of sums that up. You know, the other shapes we talk about triangles. And remember, triangles can come in a couple different ways we can see those. You can classify them, say, by their angle, where you can have a right triangle where you have a right angle in there. You can have an obtuse triangle. Oops. That's how bad I can draw triangles. You can have an obtuse triangle where you have at least an angle that's bigger than 90. And then you can have an acute triangle where all three angles are less than 90. So that's classifying them by the angles. You can classify them by the sides, where you have an equilateral triangle where all three sides are congruent. Let's see if we can draw one of those. You can have an isosceles triangle where only two sides are congruent, or two or more are congruent. And then you can have what we call a scalene triangle, like this one right here. Well, that's close to isosceles. Let's draw a scalene triangle. See if we can get one drawn. No, that's stuck on isosceles, so I'll use shape recognition again. You can have scalene where none of the sides are congruent. There we go. So right, obtuse, and acute, that's classifying by angles. Isosceles, equilateral, and then scalene, that's classifying by sides. Notice that if it's equilateral, it's also isosceles. It's just isosceles means two sides are congruent, at least two sides. Equilateral means all three sides are congruent. And there's one more we left out here on angle, classifying by angles. You could also have equal angular. That's not really used that much. Usually when you see equilateral, an equilateral triangle, you classify by its size, not so much the angles. So with that being said, you can also have, we'll talk about circles. Oops, still got it on the wrong tool there. Sorry, my computer's moving a little slow today, or I'm moving too fast for it, I don't know. So with a circle, the technical definition of a circle is that it's a set of all points that are equal distant from a central point. So we call it central point the center. And then imagine a bunch of points going all the way around here. They are all the same distance away from the center, and that distance we call it the radius. So that's like your sort of technical definition of a circle. We'll also discuss some regular polygons today. So regular polygons, really, the word regular in the sense of polygons just means that all the sides are the same. So we have our equilateral triangle. We can also call it a regular triangle. You can have your equilateral, not your regular quadrilateral, also known as a square. And then you can have it really with any amount of sides. You can have a regular pentagon with all 5 sides the same, a regular hexagon, all 6 sides the same, a regular heptagon with all 7 sides the same. You have the octagon, regular octagon, like your stop signs you see, all 8 sides the same, regular nonagon, and then you can keep going on. But these are all regular shapes. We can talk about the perimeter and area of those as well. So when we speak about area, the thing is, what does area mean? So as far as area is concerned, like if we're talking about the area of a rectangle, we're talking about how many square units will fit into a given surface. So in this case, if I started off with the outside rectangle right here, and I've got some unit of measurement, it could be feet, inches, centimeters, miles, whatever you're going to talk about. If I mark it off along one side here and mark it off the other, I get that this is a, let's see, a 13 by 5 rectangle. And we'll give it a unit measure. Let's say we measure this out to be feet. And so it's 13 feet by 5 feet. So if you're dealing with a room that's 13 feet by 5 feet, and you want to put squares in it that are 1 foot by 1 foot squares, the question is, how many squares will fit in it? And so if you were to count all these up, you would get 65 squares. So there are 65 squares that fit in here that are 1 foot by 1 foot. That is known as the area, or we say it's 65 square feet. If it were a room and let's say I wanted to put baseboard going around the bottom of it, then I would need the perimeter. And so this side would be 13 feet, this side would be 5 feet. And so I add up the outside edge, or the outside length. So I'd get 36 linear feet. 36 linear feet there. So one is a measurement of how much space you can walk around, and the other is the outside edge, the perimeter there. So area is our space that we can walk around in, I guess you could say, but it's usually it's going to be measured in square units. Perimeter is the outside edge. Now, what if you have something like a circle? What does area mean there? So with a circle, what we're saying is how many of these squares can we fit in there still? But notice when I start dragging squares in, I have a little bit more of an issue here, and that's that they don't always fit in very pretty. It happens with rectangles too. Sometimes you have like half a square that will fit in, that sort of thing. But this is a little more obvious of a problem with circles. So as I fill this in, eventually I'm going to get some that are overhanging on the circle here. So what we have to do is and I don't have a nice tool in here that can do that, but this area right here, I've got to cut it up and fill it in here. So if we were in class, we could cut that out of a piece of paper and fill those in if we want. So even though that we have to cut pieces out and then cut up this more and fill it in different spots, it's how many squares total. They don't have to be kept whole. You can cut up the squares, blend them up if you want to think about it like that, and still fill the total area inside of that circle there. So that's what we mean. We're going to talk a little bit about this. I've got a lot of resources linked for visuals as we go through this, so check out this week's resources if you want to see these visuals that I'm working with in class. So here's our first visual, and this is on GeoGebra. It's a great site for if you teach geometry and you have one-to-one devices, or if you just want to explore geometry. It's a great place to go to, geogebra.org actually, and they've got a lot of visuals here. These I didn't come up with these. I just Googled area and perimeter of rectangles, GeoGebra, and there's a lot of different examples. I just picked the ones I liked best that I thought went with the class here. So as far as this goes, we can actually go back and look at our 13 by 5. Let's see if we can lower this down to 5. Rectangle that we just saw, or you should be able to even spin it up. Let's see. Just click and drag on the corners. So let's give me a little bit of issue. There we go. I'm using a pen to control this. Earlier I used a mouse, so using a pen to, a little bit different there. So there's our 13 by 5, and you can click show the area right here, and we can see that the area is 65. You can click on show the perimeter. It shows us it's 36. But to calculate these things on your own, all we need to do, instead of counting up to squares, we can just multiply the length times the width. So the first row is 13 here. If I've got 5 of those, it's going to be 5 times 13, and that gives me the amount of squares there. So that's our general formula for calculating the area of a rectangle, is just length times width. For the perimeter, then we're going to add up all 4 sides. And some formulas you might look at might say 2 times the length and plus 2 times the width. I always think of it as adding up all 4, but if you multiply this by 2, it's like saying 5 plus 5. And if you multiply 13 by 2, it's like saying 13 plus 13. And you still get the perimeter there. So I think rectangle is pretty straightforward. Remember, that works for square as well, because a square is a subset of rectangles. And it might work with something else here that we're going to get ready to look at. So next thing we're going to look at is the area of a parallelogram. Remember, a parallelogram is a four-sided figure, a quadrilateral, with at least with both two sides. Can't talk today. With both sides parallel. So parallelograms can look like this. They can look like rhombuses. They can even be rectangles. So the area for that, let's check it out on GeoGebra as well. So here we have a parallelogram, and it has a base of 8. And so one of the properties with parallelograms is not only opposite sides parallel, they're also congruent. So if this side is 8, so is this side down here. It has a height of 5. Now height is not calculated along this slanted line, but it's a line that is connecting both the bases, and it's perpendicular to the bases. So the height is measured straight up, and it's a 5. So instead of trying to, notice these squares that are inside of this, they get chopped up like we were talking about with the circle. But if we were to take and cut this parallelogram, we make a triangle, and then it's actually a trapezoid inside of here. But watch what happens as we move this triangle over. So we can push on the slider and move it over. And it lands right there. And so now notice what we have. We have a rectangle with the length being the base there. Notice this now that I move this triangle over, it's a little more obvious that the bases are congruent in length. And the height of the parallelogram is now the height or the width of the rectangle. So you can see that animation again. You can also change the parallelogram to look like different parallelograms there. It's a little bit harder when it's this one. If we were in class, we could cut this out and then flip it around and make it a rectangle. But I don't see that as an option right in here on this animation. Maybe. No, I can't get it to work like that. But if you're in class, I'd have you cut these out on a piece of paper. It's a great activity to do. You can spin it around and see that it works there. So anyway, seeing it like that, all we really need to do to find the area of a parallelogram is just take the height and multiply it by the base. So it's still pretty much the same thing as finding the area of a rectangle. For the perimeter, we're just going to add up all four sides like you do with a rectangle as well. So let's go back and try out a few of those problems. Here's our first one. This parallelogram has a height of 12. It has this side length right here of 15, and the base is 20. See if you can figure out the area and the perimeter. So for the area, we're going to say 12 times 20. This is 12 centimeters times 20 centimeters, which is going to be 240. And notice centimeter times centimeter, treat that like a variable almost. X times x would give you x squared. Centimeter times centimeter is going to be centimeters squared. For the perimeter, notice this is going to be like a 15 and a 20 here. We can add up all four sides. So 20 plus 15 is 35, plus 20 plus 15 is going to give you a total of 70. And centimeters plus centimeters is going to give us centimeters. Like if we had 15x plus 20x plus 15x plus 20x, that would give us 70 x's. But in 7x, we just got a cm there, so it just becomes 70 centimeters. That's your perimeter. And then 240 centimeters squared is your area. Try this one out. So this one, the height, it's just spun around. If we were to take this picture and turn it, it's still the height. It's just we're counting this as our base, and that is our base, and then this is our height. So for the area, we're going to say the base, 4.7 inches times 5.7 inches. What does that give you? That gives us 26.79, and this is going to be inches squared. Area is always done in units squared, so just remember that. And then the perimeter is going to be 4.7 plus 6 plus another 4.7 plus another 6, and this is all in inches. So what is it going to give us? 10.7. So it's going to be 21.4. And this is in inches. That's our perimeter. Try this one out. So this one's kind of like what we were showing earlier on the manipulative, but we couldn't turn that triangle around. This one has a base of 0.4 and the height is outside the parallelogram. Notice if we drew this line right here, we'd still get a height of 0.3. So we can still use this. They just drew the height on the outside. In fact, if we were to slice this parallelogram right here, we could move this piece, if we were cutting it, to right here, and it would give us a nice rectangle right there to work with. So it's still the same thing, except for this time they didn't give us units, and we're going to go with the base, which is 0.4 times the height of 0.3. That's going to give us our area. So that's going to be 0.12, and whatever the units are squared. And then we are going to take, to find the perimeter, we're going to say 0.4 plus 0.5 plus 0.4 plus 0.5. It should be 1.8. So here's our perimeter, and there's our area. So then it takes us to the area of a triangle. So looking at this, we're going to start with our rectangle. Now imagine if we had that 13 by 5 rectangle again. We said the area of that was 65 units squared. But what if I had a triangle that only covered half of that rectangle? So notice the area of this triangle I just shaded in is half of the rectangle. So if I gave you a triangle, and you have a right angle right here, but if I gave you a triangle with a base of 5 and a height of 13, you could act like it's a rectangle of 5 by 13 and then simply cut your answer in half. So half of 65 is going to give us the area of the shaded triangle there. So that's going to be 32.5, whatever the units are squared. To see a better visual, we're going to look at GeoGebra here and the triangle we've got drawn. And you can take this slider right here and slide it. And notice if you take any triangle, you can make a parallelogram with it by duplicating it. Now, they also show you it's a parallelogram. If you continue sliding it, you can see how these angles are congruent, which makes it these lines right here parallel. So therefore, it's a parallelogram. So that's all that you see with those pink angles there, just to show that it's a parallelogram formed. Now remember, we just said that the area of a parallelogram is just the base times the height. So it's like you're taking the area of a parallelogram and cutting it in half. And this is set up so that you can really make this almost any triangle you can think of out there by dragging the corners around. And then you can slide it and make another parallelogram whenever you need to there. So in general, our area for a triangle is 1/2 times the base times the height. For a parallelogram, we said it was base times height. So a triangle is half of that. For the perimeter, we're just going to add up the 3 sides if we have it there. So if we're going to say that our area of the triangle is 1/2 times the base times the height, we need to talk about what do we mean by when we say the height of a triangle. So every triangle has 3 heights. And so to define it, what we want to say is that basically you're going to pick one of the corners and you're going to draw a line to the opposite side so that it meets at a right angle. So I wouldn't draw a line going to the opposite side like this because it doesn't meet this side at a right angle. It's going to be right around in here. In fact, if this is a right triangle, then the height here would be on the triangle side there. Notice it goes from this corner to the opposite side, meets at a right angle. That means if I'm calling this the height, this is the base. But there are a couple of other heights in this triangle as well. We could look at the height. Let's pick a different color. We could pick at the height going from this corner to the opposite side. None of those make a right angle. Oh, it makes a right angle right here. If we're talking about the red that's going on, then this would be the height and this would be the base. But there's one more height to it. Let's change to a different color. Let's go with, we'll go with purple this time. If I pick this corner and went to the opposite side where it meets at a right angle, then what's drawn in purple here, this would be the height, and then this side right here would be my base. So every triangle has three heights to it you could look at, and the bases are always perpendicular to them. Sometimes the height is on the triangle, sometimes it's inside. Like, let's look at another example, and typically when we're talking about area, we're only going to use one of those heights, because once you got a height and a base, that's all you really need. But it could be drawn, three different ways for each triangle. So for this one, here's an isosceles triangle. Two sides are the same, and I'm going to draw the height of it on the inside. So starting right here and going down, it's going to meet at a right angle right here. This is my height, this is my base. And then sometimes we have the height on the outside of it. So if I pick this corner, notice no matter what part of the side I draw it to over there, it never meets at a right angle. So if we want to get more technical with our definition of what a height to a triangle is, it's going to meet the line that contains the opposite side. So if I made this base, if I drew the line that contained it, remember lines go on forever, this is the line that contains the opposite side, then I can draw my height, and it goes from this corner till it meets at a right angle down here. This is my height, even though it's on the outside. So sometimes we have the height on the triangle, sometimes we have it on the inside, and then sometimes we have it on the outside of the triangle. We could also draw a height right here that meets this base, if we call this side the base, that's inside, but a lot of times on these obtuse triangles we'll see it on the outside. Like, take a look at this one. So this one, I know the base is 10, and then if we add the height right here, boom, like that, it's dashed lines, not part of the shape, it's just showing you this is the line that contains the opposite side. This is our height of 5 here. So to calculate the area of this triangle, we're going to say area is equal to 1/2 times the base times the height. The base is 10, the height is 5. And so the area is going to equal 5 times 5, which is 25. And to find the perimeter, I would need to know this side and this side right here. I don't have enough information to find that right now, so we're not going to find the perimeter of that triangle. Let's take a look at this one. This one, we can find the area and perimeter of it. So try out, pause the video, try this one out. So for this one, notice that I can't count this as the base because then I would need that right there to find the height. But if I count this as the base, this would be the height. But I got to figure out what this height right here is. So since it's a right triangle and I know two sides, I can use the Pythagorean theorem. So in this case, h is the unknown side. I've got h squared plus 20 squared equals 25 squared. Solving for h, I get h to be 15. So the height here is 15. For my perimeter, the perimeter is going to be all three sides added up. So I get 20 plus 15 is 35, and then 35 plus 25 gives me 60. For the area, I'm going to say 1/2 times the base of 20 times the height of 15. That's going to be the area of the triangle. So I end up with 150. They didn't give us any units here, so if it were feet, it'd be feet squared for area and just feet for perimeter, but no units attached to that one. This one, we don't have enough to figure out the perimeter, but we can figure out the area. This is our base, it's 30. This is our height, it's 8. And then we're going to times that by 1/2. That will equal our area. So we end up with 120 is the area for the one on the right. For the area of a trapezoid, we're going to take a look at GeoGebra again. Remember, a trapezoid, you've got two bases. In this case, we labeled this one base 1, and this is base 2. They're going to be different lengths, and then you've got those bases should be parallel. And then the other two sides, we call them the legs, and they will not be parallel. That's what makes it a trapezoid. Only one side is going to be parallel there. Now, as we look at this, we have an isosceles trapezoid here, meaning that these two legs are congruent. So this is a great demonstration because we've got, remember, this is base 1, it's 2, this is base 2, its length is 6. You can count them on the squares here. If you drag this slider right here for the hint, check this out. They're going to take that trapezoid and they're going to flip it around like that. So what's formed here? What's formed is a parallelogram. And notice that because this base got moved up here, the length of this side is now 8, and the length of this side down here is also 8, and these sides right here are now parallel. So if you found out the area of this parallelogram, in this case it would be 8 times 3 times, well, it's just 8 times 3, but then notice you've got two trapezoids. We only want to know the area of one trapezoid. We multiply it by 1/2, the area of the parallelogram by 1/2, and you get the area of the trapezoid. Let me say that again. Find the area of the parallelogram here, formed by making the two trapezoids. So if you find the area of the parallelogram, you're going to cut it in half to get the area of the trapezoid. How do you find the area of the parallelogram? Base times height. How do you find the area of the trapezoid? Base times height times 1/2, meaning base of this parallelogram. So notice that our base of the parallelogram is made up by base 2 and base 1. So let's go back to the drawing so I can have something to write on. So let's draw out I can't talk today, our trapezoid. Right there it is. And this has, we'll call this base 1, and this is base 2. And that's what I want to know the area of. In fact, let's shade it in. There we go. I want to know what the area of that shaded region is. And then if I were to, let's say, duplicate that trapezoid, let's do another one here. Where's my paste button? So this is the same trapezoid, but this time I'm going to spin it around like this. This is all that Visual and GeoGebra was doing. Then we can say, okay, the top right here, base 1 is now down here, and base 2 is now up here, and our height is right here. That's h, our height. So the area of the parallelogram is base 1 plus base 2 of the trapezoid. Those two add up, give you the base of the trapezoid times the height. But I'm not finding the area of a parallelogram. I want to know the area of the shaded region. It's going to be half the parallelogram, so times 1/2. There's your area for a trapezoid. And I don't want to spend too much more time on this, but if you go back and look, you say, well, what about non-isosceles trapezoids? Let's change it up. You can drag this corner and make it a different trapezoid. There's a trapezoid. And you can, whoops, let's go back. You can drag it again and see the same thing happens. We get another parallelogram when we switch that around. Okay? So that's what we're going to be doing. Once again, for finding the area of the parallelogram, but to find the perimeter, we're going to add up the sides like we did with other quadrilaterals. So try this one out. See if you can find the area of this trapezoid right here. So for this one, I'm going to say base 1 plus base 2 times the height times 1/2. So here's, you can call it base 1 or base 2, it doesn't matter. Base 1, here's my height. So we've got 8 plus 10 times the height times 1/2. So you get 18 times 4 times 1/2, or 36, and this is in meters squared. That's your area. Here's one. Nevada itself, the state of Nevada, is pretty close to a trapezoid. So let's see if we can find out the square mileage of Nevada. So for this one, notice our parallel sides here are going vertical, but we can still find the area using that same formula. So this is going to be base 1, base 2, this is my height. So 1/2 times the height, and then base 1 plus base 2. And for me, it's easier to multiply 1/2 times 7/16 because I know Half of 700 is 350. Half of 16 is 8, so this would be 358. But for this operation, we can do it in the calculator, or we can do one of these, just to kind of bring up something we've already talked about in class. Remember this trick? The lattice multiplication. So it should work for this. Let's try it out. 3 times 9 is 27. 3 times 0 is 0. 3 times 3 is 9. 45, 0, 15. 72, 0, 24. And then add along the diagonals here. Let's extend our diagonal sum. So we get a 2, 12, carry the 1, 8, 12, 16, carry the 1, 3, 8, 10, carry the 1, and we end up with 11 right here. So I got 110622, and this is in miles squared. Now you don't have to do lattice multiplication for this. You can use your calculator, but I like to bring it up every once in a while just to remind you before the final. Try this trapezoid out. So for this one, we're going to say 21 plus 38 times 16 times 1/2. So I get 59 times 16 times 1/2, or 8 times 59. Do a little mental math here. What I'm thinking of is, what is 8 times 60? 8 times 60 is going to be 480. But that's one more 8 than I needed, so I'm going to subtract 8 from it and get 472. So 472, and this is in inches. Let's write it out like that. 472 inches squared. That's the area. Make sure you're including units and the correct units, squared units if you're talking about area, if that's what they're asking for. Now, for areas of regular polygons, it's a little more complicated, but really, if you can take the area of a triangle, you should be able to do the area of a regular polygon, or at least what I'm going to ask for you to do in this class. So imagine we have pretty much any regular polygon. I'm going to look at this one. This one has 1, 2, 3, 4, 5, 6, 7 sides, so it's a regular heptagon. And imagine breaking that heptagon up into triangles stemming from the center. Now, these triangles are all the same. So you cut them up, and since this side is the same on all of them, and they're all the vertices are the same distance away from the center of that shape, they're going to be congruent triangles by side, side, side. So if I find the area of one triangle and multiply it by the number of triangles I have, then I got the area of the shape. So to find that area, I need to know a couple of things. I need to know what this side length here is here, and I need to know the height. So for this class, I'm going to give you the height. So for instance, let's say we had a height. Let's see if I can change the color right here, and it was length 5. I'm giving you the side of that regular heptagon is 3. We can find the area of this triangle right here by saying 1/2 times 3 times 5. Remember, the area of a triangle is base times height times 1/2. And so I get 7.5. So the area of the green shaded region is 7.5 units squared, and I've got 7 triangles in here, so I'm going to multiply that by 7. So 7 times 5 is 35, 7 times 7 is 49, plus 3 gives me 52. So 52.5 units squared is the area of that heptagon. And so this is the technique you'll use for any other regular polygons. I'll give you the side length, I'll give you the height. In my geometry class, when we have more time to go through it, I usually make them find the height at some point. They should be able to find this angle out on their own. Draw this line, make a 90-degree angle, use trigonometry to figure out the side lengths. So get a little more involved if we have more time. But in this class, I'm not going to make you do that. I just want you to understand that we can break a regular polygon up into triangles, or decompose it into triangles, find the area of each triangle and add them up. So it doesn't matter the shape. You can have a hexagon. I think this is a 10-sided figure. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so it can be a decagon. Any of them, you've got 10 sides, you're going to have 10 triangles. You got 6 sides, you're going to have 6 triangles. You will have this line in there, so it looks like it's twice as many triangles, but we're just really taking this as the height and then finding the area of this triangle right here. Then we're going to get to area and circumference of a circle. So once again, we discussed what we meant by the area of a circle. Circumference is the equivalence to perimeter in terms of circles. They're not, it's not a polygon, but it's, if we were to cut this out and roll it out, how long would that, say, edge be when we rolled it out? So still the same thing. Distance on the outside is our circumference. So to get a better visual, let's go back to GeoGebra. So here we have a circle with a radius of r, and we're going to straighten that out. So that's what I mean by circumference, is what would be this distance right there. So in this case, anytime we want to figure out what that distance is, it's 2 times pi times the radius. So 2 times pi times the radius will give us the circumference. So if we're looking at, let's look at a few problems right here. Here's some circles, and I'm going to come back. Actually, we'll do it now. We'll go ahead and do both of these, or all three of them, I mean. If we're looking at this one, if we want to know the circumference, circumference equals 2 times pi times the radius. The radius is 4, so 2 times pi times r equals circumference, or let's change that to 4. So 8 pi is the circumference. Now, if I tell you to leave it in terms of pi, it means don't calculate out pi there. Just leave it like it is. Or I may say use 3.14 for pi, and in that case you punch in your calculator 8 times 3.14. Let's look at this one. If we have circumference equals 2 pi r, then the r here is 10, so you get c equals 2 pi 10, or 20 pi equals your circumference. I could have also given you this problem written backwards. So instead of giving you the radius is 10, I could have said, suppose the circumference is 20 pi, find out the radius. So in that case, we work backwards using the same formula. Circumference equals 2 times pi times the radius. You know circumference here is 20 pi, so that equals 2 pi r. Divide both sides by 2, you get 10 pi equals pi times the radius. Divide both sides by pi, and you get 10 equals the radius. So sometimes we give you the radius, find the circumference, but we could also work backwards from that. Now, to talk about area, let's wrap this thing back up. We're going to dissect the circle into small pieces. So let's suppose we have this. We're going to cut it up into 6 slices. And then we're going to straighten out the circumference. So this length right here is 2 pi r. And it says rearrange right here. Let's rearrange it some. So this is just going to unfold your circle. And it lands like that. And if we continue to unfold it, and we're going to actually move this back to fit in the pieces over here, you get this right here. So notice our radius is right here. That's the height from here to here. And this side right here is half of the circumference, or just pi times r. Now, that's not quite a recognizable shape because, if we zoom in, we kind of see that this isn't a polygon yet. So let's move that back into a circle. Whoops. So go back to a circle. And instead of dissecting it into 6 parts, you can make it 14, 42, 122 parts. I'm just cutting up that circle into more slices. It'll go up to 200 parts right there. And so that's what I'm going to do. I'm going to take and now drag it out. And then I'm going to take this blue side and fit it into the red side over here. Looks like a comb, doesn't it? And now if I zoom in, notice what I have. I've got a rectangle with a height of r, that's your radius, and a length of half the circumference. So let's look at that in somewhere I can write. So I made a rectangle. Whoops, not a circle. I made a rectangle by spreading that circle out. And the height is r. And this is 1/2 of the circumference, this side right here. Because remember, it flopped out and then we fit it back in. So the circumference is equal to 2 pi r, right? So 1/2 times 2 pi r just gives you 1 pi r. And so the area of this rectangle is pi r times r, which equals pi r squared, which is the area of the circle there. That means area, and usually circle is just when we write out circle, we just draw a circle with a little dot in the center there. So the area of the circle is pi r squared. Now you could just give that to you, and maybe you didn't enjoy that explanation any, but I think if you're going to teach this, this is one of the most meaningful of the GeoGebra demonstrations here, is to be able to show that you can unfold a circle as you cut up into tinier and tinier slices, or more and more slices. You can unfold it and rearrange it into a rectangle with a height of r and a length of pi r, and then now the area of a circle makes sense. It's pi r squared. So if we look back at this pair of circles over here, if we want to know the area, area is pi times the radius squared. 4 squared is 16, so you get 16 pi for your area. Over here, area is pi r squared, so you get pi times 10 squared. So the area is going to be 100 pi. And of course, this area will be the same because it's got the same radius. Sometimes I want to give you a little bit more of a challenge than just your typical find the area of a circle. So these last few problems I'm going to take you through is just seeing if you can figure out the puzzle. So in this case, we've got two circles. I want you to find the area of this white circle there. It almost looks like a moon shape. Not the rectangle. The rectangle is just so I can write somewhere you can see me writing, but just the white shape over here. This is the center of the larger circle. This is the center of the darkened circle. The radius of the darkened circle is 3. All right, so let's see if you try that out. If I want to find the diameter of the black circle, well, the radius is 3, so that's going to be 3 as well. And so the area of the dark circle is going to be pi times the radius squared. Now, I figured out that other section, so I knew the radius of the large circle, but I'm going to go ahead and figure out the radius, the area of the smaller circle. So you got pi times the radius squared, or pi times 3 squared, which is 9 pi. So I now want to find out the area. This is the black circle right here. Now I want to find out the area of the white circle. So the area of the white circle is once again pi r squared. So 6 squared is 36. So you got 36 pi is the area of the white circle. And so if I take the area of the white minus the area of the black, we get 36 pi minus 9 pi, which is 27 pi. So 27 pi is the area of that weird white moon shape there. Try this one out. Find the area of the shaded region. All right, I take you paused it and gave that one a good try. Notice that if I draw the diameter of this circle, I can figure out the radius of it because the height of the rectangle is 5, so the diameter of the circle is 5, which means the radius must be 2.5. The area of the rectangle is going to be 5 times 10, or 50 units squared. So this is area of rectangle. Now I need to find the area of the circle. The area of the circle is going to be 2.5 squared times pi. So this gives me 6.25 times pi. And for this case, since I want to know the area of the shaded region, it kind of helps to figure out what is 3.14 times 6.25. which gives me 19.625. I just punched that in my calculator. And then I'm going to take 50 minus 19.625 to find the area of the shaded region. And I get 30.375. There's your area of the shaded region. All right, and this one right here, the area of the shaded region is what we're looking for again. I know it can look a little scary when we start to see it like this. Remember that this radius is 10. That's the radius of the larger circle there. So we want to know the area of the shaded region. So my plan is to find the area of the big circle. Then subtract the area of the square, and then add the area of the small circle. So that's what I want to do. So the radius of the big circle is 10. So the area is going to be pi times the radius squared. So 100 pi equals the area of the big circle. Or since we're going to add the area of a square, it might be helpful to go ahead and put this in decimal form. 3.14 times 100. Remember, anytime we multiply something by 100, we're just going to move the decimal over 2 spots. It's going to be 314. Now, to figure out the rest of it, we're going to have to combine some information about trig. This is like the most high-level thinking I'm going to have you do, and it's not really something I'll put on a quiz or anything as far as doing this much trig and understanding of triangles. If we had more time, I'd definitely put it on there, but I wanted to throw it out as a challenge. If we look at this shape right here that I'm highlighting, in fact, let's color it in with a highlighter. I get a triangle. Let's see. And I'm giving you that this shape is a square we want to find the area of. But in this triangle right here itself, we know that it's a right triangle because this is part of the diagonals of a square, so they meet at a right angle. And that it's isosceles because the radius of a circle is the same no matter where you draw it on this larger circle. These two sides must be congruent, which makes this a 45-degree angle here and a 45-degree angle here. So let's redraw that triangle so it's a little bit easier to understand. I'm just going to draw it right here. And so it's got a right angle. This side, let's see, right here is 10. And so is this side. And this is a 45-degree angle. So with that being the case, I can say, let's suppose we're talking about this angle. This side is your opposite side. And this side is your hypotenuse. We want to know what the hypotenuse is, so that way we can figure out the area of the square. So we're going to use trig here. Which trig function we're going to use? We're going to use the sine function, because sine deals with opposite over hypotenuse. So the sine of 45 equals the opposite over the hypotenuse. Use the Switchum property we talked about in the trig lesson, and we get 10 divided by the sine of 45. That gives me 11.75. Now, in my calculator, I actually got 11.752214. I'll leave it like that because in the calculator, I'll leave it like that because it gives me a more exact value. So I now know the side of the square there. And so this is also going to be 11.75. And the area will be that value squared. So I'm going to use the value of my calculator, which is 11.752214, and that's what I'm going to square. And I get 138.11. Now, I need to know what is the radius of the smaller circle. Let me clean this up so we can look at it better. So we can't just assume that the red line right here is being cut in half. In fact, it's not. But what we can do is notice that the height of this, here, let's draw a line. The height of the square is also the diameter of the smaller circle. So if I take half of 11.75, or In the calculator, I had 11.752214. Times that by 1/2. I get 5.88. That is my radius. Even right here, it's 5.88. So it's a little bit larger than half of 10 there. So now I can take 5.88 and put it into my area of a circle. So area equals pi times 5.88 squared. And then I get 34.57. I'm going to times that by 3.14. And I get the area of the small circle is 108.56. So 108.56. So I'm going to take 314, that's the area of the big circle, minus 138.11, that's the area of the square, plus 108.56. And I get the area of the shaded region, my final answer here, to be 284.45. All right, and I know this was a long lesson today. We're approaching an hour already, but we went through different types of shapes, what they were, what area meant, what perimeter means, and how to calculate the area and perimeter of a lot of different shapes there. I want to go through in detail because, like I said, I don't know, some of you, this might be super easy to you, and you're like, I got this. Some of you may be like, you know what, I want to understand at a deeper level, and other people may just be struggling with the basics of finding area. So my audience is different each semester, so I want to give you a detailed review there. Let me know if you have any questions, especially on your homework or as you prep for the quiz or final exam. And thanks for working hard and sticking with me for an hour. I'm not feeling too well today, so I know that I must be a little more drier than usual, but hopefully you can follow along and you're not asleep yet. All right. Thanks for watching. Thanks for hanging in there, and have a good day.